Hello, good morning. This is Dr. K. Kannan, Associate Professor, Department of ECE, RMK, College of Engineering and Technology. In this lecture video, I am going to talk about the noise in communication systems. So, how to determine the noise level in communication system? So, the noise effect can be determined by measuring or calculating the signal to noise ratio SNR in the form of analog system and probability of error or bit error rate BER for digital system. So in analog system we can measure the noise level by SNR, and in digital system it is a bit error rate. So to determine the quality of the received signal at the receiver, that means at an antenna, signal to noise ratio at the input and at the output of the receiver SNR suffix O, that is O represents output, I represents input. So by in this way we can measure the quality of the received signal. So S by N it is input side, S by N out it is output side. So SNR out is always less than SNR because the existence of noise in the receiver itself. Then I have to go for noise calculation. SNR is the ratio of the signal power to the noise power. So SNR equal to, in terms of decibel, 10 log base 10 of S by N. Then the noise figure we can represent in terms of value by taking the ratio of signal power to the noise power at the input divided by signal power and the noise power at the output in terms of a decibel. So noise factor in terms of value, NF equal to 10 log base 10 of F. So F equal to 1 for noiseless network, and in general if always capital F is greater than 1. The lower the value of F, then the networks or any system, it is a better output. Then additive white Gaussian noise. So additive white Gaussian noise is where the noise is usually additive in nature and it is added to the signal as shown below. Look at the diagram where the signal is getting added with the noise when the signal is transmitted in the channel, and the receiver side we can have the original signal plus noise. Then as I told you already, white noise means the spectrum is uniform for the entire frequency, white noise. Then what about the Gaussian? So we generally assume that the noise voltage amplitude have the Gaussian in nature, or in another way we can say that it is a normal distribution. Then we go for narrowband noise. When additive white Gaussian noise signal passed through the bandpass filter, then the resulting output is called a narrowband noise. To find the effect of noise signal in a amplitude modulation, double sideband suppressed carrier or double sideband full carrier, and single sideband transmission, noise should be considered as additive white Gaussian noise and another one narrowband noise. So time domain representation of the narrowband noise is given by n of t equal to nc of t cos 2 pi fct plus nq of t sin 2 pi fct, where nc it is a cosine term and nq it is a quadrature term. Then we can represent NCQ, it is a low pass signal and it is in phase, and Q represent it is a quadrature phase component of N of T. Then we have perspective density of additive white Gaussian noise affecting the AM and double sideband suppressed carrier. So look at the diagram where we can have omega c, it is a angular frequency. So in the right side and the left side you have both a bandwidth of equal width. So the noise power capital N equal to 2B into N naught by 2 into 2. So the 2 get cancelled. Finally we have 2 N naught into B. Then possibility density of additive white Gaussian noise affecting the single sideband, where we can have only one sideband in the both the side, right side and the left side, so that the noise power N is equal to B into N naught by 2 into 2, so that it is N naught into B. The total effect of AWGN signal on AM and SSB and DSB is due to the component of, as the effect of quadrature component is 0. Then possible density of the additive white Gaussian noise affecting the message signal, so limited bandwidth spectrum, so where we can have the noise power is N equal to B into N naught by 2 into 2, it is N naught B watts. Thank you one and all.